Okay, hello everyone, thank you for coming. Hi, my name is Matt. I work for JetBrains. I'm a developer advocate and I work on Rider, which is our cross-platform IDE. I work as a developer advocate. I do a bit of development as well. I do work with some of the Unity support that we have in Rider. And today I'm going to talk to you about writing allocation-free code in C#. This is kind of a topic which is a little bit trendy right now. It's a bit cool. Lots of people are talking about it. And doing it is becoming a bit sort of fashionable. And I'm going to start with a slide which is kind of beginning to get a little bit traditional in my kind of talks here. The big question really is, how do I go about writing allocation-free code in C#? And the simple answer is don't. It's not there. You're not going to need this, unless you actually do need this. And the key point here, this is the sort of the main thing I want you to take away from this talk. So I'm going to talk about some nice geeky things in a minute, but this is the important thing there. Always make sure you are measuring what's going on here. So I'm going to tell you some things here about writing allocation-free code, why you might want to do that, how it can help you and everything, but the only time it's really useful is if you measure and you know it's going to help you. So, okay, why? Why am I talking about allocation-free code in C#? We're used to a managed memory system. C# handles all of our memory for us. And the idea is roughly, that managed memory is cheap. This isn't strictly true. Allocation is cheap. Garbage collection is expensive. Garbage collection, we have to stop things, scan for objects that are being used, clean them up, reallocate the memory, and carry on again. So it's kind of expensive. And when we're talking about managed memory, we're all used to the idea of memory leaks and not using too much memory and trying to keep your memory low. But one thing we don't necessarily concentrate on is memory traffic, is throughput. This is the idea of, well, what do I mean by throughput, really? It's more allocations. But using more allocations means more garbage collections. More garbage collections introduce pauses. Pauses disrupt then your throughput. And better throughput means that your application is smoother. It doesn't necessarily mean it's faster. It probably will be, but it's generally going to be smoother. And this is good then for low latency type applications, things like games or servers or interactive user interfaces. So, if it's a server, you can serve your pages without pauses. If it's a video game, you don't want to be sort of firing and shooting, about to attack somebody, and the game pauses and stops and stutters. And the same with interactive user interfaces. You want those to be smooth and responsive. And when you kind of look at that list, it is basically, that applies to a lot of the applications that you write. And it's also very important then if you think about a constrained environment. So if you're talking about a mobile device or a game console or something, using less memory is a good thing. If you've got a less powerful device, then garbage collection can be slower, and so your pauses can be more obvious. And of course, if you're doing fewer garbage collections, that's going to be good for battery life as well. And so it all comes back to throughput. And again, the whole point is if you're doing gaming, mobile gaming is huge. And so if you're in a constrained environment with gaming and throughput, you want everything to be running smoothly and nicely. And another good reason for why you might want to know this is that even if you don't use it, you're still going to be using it through the platform. The platform itself, C#, the base class libraries, they are going to be using this kind of stuff here, so it's useful that you know what's going on. And this has been more important recently because performance has become a key part of the design of the platform. So .NET Core has a distinct focus on performance and on building things so that they can perform well. And examples of this are when C# added tuples. They didn't use the existing system.tuple class. They introduced a new type, system.valueTuple. And this is not a class, but a struct. And again, this is all about being memory efficient. There's a similar thing with the await for each feature in C# 8. This is going to be based not on task of T, but on value task, again, because it's a struct rather than a class. And it's especially important then for span of T, which we'll talk about later in slicing, and being memory efficient while you're using this. Okay, so we'll have a look at some low-hanging fruit, which I think might be a particularly British saying there, if you're going to pick some apples, easiest to pull the low-hanging fruit. There are a couple of things you can do. There's a number of things here, really. You can do then to sort of reduce the amount of allocations you've got in your code. And there's some very simple things here. So object reuse. If you've already got an array allocated, pass it back in, reuse it, rather than creating a new one. Avoid string concatenation. Using string builders, reusing string builders, and so on. There are a few others there. Params. Params is a good one here, because params kind of shows you that there's some unexpected allocations going on that the compiler does for you. And so there are things happening here where you don't necessarily see it in your code, but it's still happening. So if you have a params method on the side there, is taking in a string array, you might be calling it with just 2 parameters. But behind the scenes, the compiler is allocating an array for you. When you're passing in 0 parameters, the compiler is still allocating an array for you, and it allocates it every single time. Except it doesn't, I've just lied to you, it doesn't create it every single time. Newer compilers, newer frameworks will pass in array.empty. And this is a static instance which is shared across the platform. So again, it's very, very important that you don't necessarily trust what I'm saying here. You measure, make sure that the things that I'm telling you are useful in your use cases. Okay, so boxing is another one where we have these potentially hidden allocations that are going on. So this is passing a value type to a method that's expecting a reference type. And what has to happen here is that the runtime will create a new object on the heap, copy the value type into that, and carry on working on that. And this is important to know because any changes you make to this boxed value don't affect the original one. And so there's an allocation going on here which you might not necessarily spot. There are tools that can help. So ReSharper and Rider have got a very useful plugin called the Heap Allocation Viewer, which will sort of pull these things up. It'll recognize when there is a boxing going on, and it'll show that for you. But let's kind of step back a little bit here. I've been talking about reference types and value types, so let's kind of refresh our memories of what these mean. So if we have a reference type, this is the class keyword. Value types, it's the struct keyword. We're all familiar with this. Reference types are allocated on the heap, whereas value types are allocated on the stack. They can also be embedded inside a reference object as well, but generally they are allocated on the stack. If you have a reference type, a variable for a reference type is a reference to the thing on the heap. So a variable to a reference type is pointing to the heap, it's saying it's over there, that's where the object is. Whereas if you've got a value type, a variable of the value type, it's the thing itself. It's an integer, it's a vector, it's whatever it is, it's the actual data. When you pass a reference type to a function, to a method, it's passed around by reference. The object's still over there on the heap. You don't pass the object itself around, you say it's over there on the heap. Whereas with value types, it's passed around by value, which means that it's copied. So you copy the whole thing. If you've got a thing which is an integer or a vector, it gets copied around and it gets copied to the new method. Assignment as well is important. When you assign a reference, when you assign a reference to a value, to a variable, you're making a copy of the reference, not the object. So the object is still living there on the heap. You just got a new variable saying it's still over there on the heap. Whereas with a value type, when you make an assignment, that makes a copy of it again. So you end up with 2 copies of the whole data. That's what do we mean by heap and stack. There's a bit of a refresher on heap and stack as well. So the heap is general purpose memory. The key thing there is that it lasts for the lifetime of the application. You can allocate stuff there and it'll stay there for however long you're using it for. The stack, however, is a block of memory which is purely for data required by methods. So when a method starts, it pushes some space onto the stack for local variables. It uses that data throughout the lifetime of the method, and when the method finishes, it pops the stack and cleans away all those allocations. Value types are the whole data itself, and so they can live directly on the stack. So when you put some space in there for the stack, all the data for that object lives in that stack. There are things you can do with that as well. You can use the stack alloc keyword to create a block of memory on the stack, which is used aside from your variables. And so you can use it then for lots of other data you want to, and it's quite useful. But the key point really is that allocation and cleanup is cheap because you've got this stack. When the lifetime of the method is over, it gets cleaned up. So it's cheap, but you are limited by space. Okay, so let's jump back then to a couple of the other things which are going to be sort of hidden allocations for you. You've got things like closures. Closures, again, the compiler is doing things behind the scenes which will cause allocations. It rewrites all of this to capture the local variables into a class, and the lambda is written as a method on this class, and the class itself is allocated when you need to use it. Link does a very similar sort of thing. And of course, it internally has classes then which represents the enumeration, and so there are allocations going on here. And again, the heap allocation viewer plugin can show these things, can show where it's being used, show that you're capturing, for example, the name parameter there. A similar thing with iterators. The code is rewritten to a state machine, and the state machine gets allocated and called again and again as the method goes through. And also with async await, we get a state machine created here, it's allocated, we get a task method builder allocated, and then there are more allocations as well. When you need to do a task, when you need the result is stored in a task or a task of T that is allocated and used. And this can be expensive for common use cases, which could be things like a synchronous return value. So if you already know what the result is. Yes. Result is, and we're back. I'll just shout. Yeah, common use cases. Common use cases. If you already know what the result of an asynchronous operation is going to be, you still have to allocate a task for it, and you don't get the chance to reuse things, and you're just having more allocations then for something which, if you wrote in a non-asynchronous manner, would be much cheaper. And there's some useful things here. There's a new type value task, which is, it's a struct, which makes things a whole lot easier. And it's really good for these kind of common use cases of when you have an immediate return value there, you're not over-allocating what you need to use. So there's a number of things there you can do which are quite useful, and there are workarounds for these kinds of things as well. So for example, if you have params, you can introduce overloads with a common number of arguments there, which can avoid that array allocation. If you've got boxing, you can introduce generic overloads, because the generic types can then let the type system work for you and handle the value types nice and easily. If you've got closures, you can avoid them in your critical paths. So if you've got some piece of code which is going to get called very, very frequently, then avoid the closures, so you're not allocating these state objects. You can pass the state in as arguments rather than having to capture it in a class. And another thing which is really cool as well is to investigate local functions. Local functions are very similar to how closures work, but the class which is allocated to, the type which is allocated to hold the data is not a class, but a struct. And so again, you could avoid allocations at that point. A similar sort of thing for link. If you have a very sort of critical piece of code which is being called again and again and again, you might want to avoid link there and just use if and for each. Iterators, you've got a couple of options here. Iterators are very, very useful. It's hard to give a sort of a blanket bit of advice on how to replace those. Perhaps you want to replace that with a simple collection, an array, for example, or something. But the important thing here is to be aware that there is a cost with iterators, and have a look then to see if you can mitigate that cost. And again, with async await, the value task is a very useful type which you can use for asynchronous code. But that's kind of low-hanging fruit. That's the kind of stuff which is fairly straightforward and nice and easy, which you can look at. What I really want to talk about, though, is reference semantics with value types. What? What does that mean? It's like, it's fine, it's okay. It's a number of collections, a number of features which are introduced in C# 7.2, which will allow you to, which work together really to deliver a really nice way of working with value types. So we've got things like in parameters, ref locals and ref returns, read-only ref returns, and read-only structs, proper immutability, and reference structs as well. But let's back up a second here. What does this actually mean? What does reference semantics with value types mean? The idea is that allocating a reference type has a cost because of garbage collection and so on, but passing it around is cheap because you only have to pass around a reference. It's over there on the heap. You get to use it. But allocating a value type is cheap because it lives on the stack and it can get cleaned up, and it can get cleaned up very easily. But passing it around has a cost because you have to make copies of it. And the downside as well is that when you make a copy of something, you are not working on the original value. So it's now hard to make changes to it. So why can't we have the best of both worlds? Why can't it be cheap to allocate and cheap to pass around? And that's exactly what this set of features does for us. So basically, it allows us to use value types in the same way that we would use reference types. We get to pass by reference everywhere, basically, which is very, very useful. We can now sort of replace some of our reference types with value types. And this allows us to reduce our number of allocations. Reducing the allocations then reduces the memory traffic, which can then reduce the number of garbage collections, which can then obviously improve our throughput. So passing by reference then allows us also to avoid copies. And that allows us to sort of modify things as well, so we can use our structs. We've always been able to pass structs into functions, but now these set of features altogether allow us to work much nicely with it and enable us to sort of modify data and work well with value types. And it's important to point out as well that these are generally rather low-level micro-optimizations. So again, you're possibly not going to use them directly yourself, but you'll be using features which then use it as well. They'll be used in the platform. But then there's going to be scenarios where it's going to make a whole lot of use, a whole lot of sense to use. So games, it's going to be very, very useful if you're writing games, for example. Also things like parsing or serialization and so on. There's going to end up being a lot of uses for this kind of features. OK. I've been talking about passing by reference and passing by value, so let's just kind of have a refresher as to what this means as well and how we can make use of this. If we have a variable for a reference type, this is actually a reference to the object on the heap. It's over here. Passing a reference type to a method is just passing this reference. So the caller method and the called method still see the same object. It's this object over here on the heap. A variable for a value type is the value itself. It's the actual value. So if you pass that to a method, it makes a copy of the value, so you end up with two. If you assign the a value type to a new variable, it also makes a copy. And that means then you've got two different copies. If you make any modifications, the original value is unchanged. It's also worth pointing out is that even though I'm talking about performance and we're trying to reduce these number of copies, the copies aren't actually that expensive. You know, if you're just trying to copy an integer as a value type, that's fine. It's not a problem. If you've got a vector which is going to be 3 integers, again, it's not really a problem. So again, low-level micro-optimizations, but put together in a sort of very hot path, very critical path, this can make a difference. Right, so the first of the small features which kind of build together, give us all of our reference semantics, is the idea of ref return. C# 7.0 added this, and the idea is that you can return a reference to a value type rather than a copy of it. So for example, if you had a method which returned you back a point, which was going to be, say, 3 floats, you know, an XYZ thing there, you could return back a reference to this point rather than the point itself. The lifetime of this value, therefore, has to be larger than the called method. So you can't return back a variable used in the called method because your stack's been cleaned and that object has gone. So it has to be a reference to a field or a reference to something which was passed into the method in the first place. Modifying the reference that you get back is the same as modifying the original value because it is the original value. is a reference to that value there. So they are the shared thing. This enables some very useful features because you can do things like returning back a reference to an array cell and update it as a field. Not as a field, sorry, as a variable. So I could return back, I could have an array of data, I could return back a reference to one particular element in that array, and I can modify it, and it would be that particular bit of data that was modified. The way to use it is to simply add a ref modifier to the method declaration return type and to the return statement itself at the end of the function. But then how do you use it? Because if I get returned back a ref return from a ref return, I try and assign that to an actual variable. That variable is going to be declared as an instance of the value type itself and not a reference, so it'll get a copy. So for example, if I'm returning back a reference to an int, if I try and assign that to an int, they're two different things, and so it'll end up copying it. And so we have the second feature, which is a ref local, and that's just a variable that is a reference to a value type. And again, accessing that variable gets the original value. It is the same value. And so you use the ref local to store the ref return result. And the way you use this is to use the ref keyword again. And type inferencing, you have to use ref var rather than just var, because var will be the value type itself and not the ref modifier. Okay, so let's have a look at how this works. So I have a small example here, simple example, which is going to be a 2D point with an x and y value, public values. They're mutable, they can be changed. I'm going to pass this into my enemy class, and it's going to keep it as a field. And I have two methods. One is to get me the location, and then the other one is to get the location by ref. The one which is by ref is just using a ref keyword in the method declaration and also in the return statement. If we have a look at the first usage there, I'm creating an instance of an enemy and passing in a point to it, and then I call getLocation. And here now I'm assigning that to a point that is a copy of the value. If I change the value there and I set it to be 12, that changes my copy. It doesn't change the original value. And I can test that here and assert that. And if I run that test, there we go, we're good, we're green. So we can see that I've modified my local copy of the struct, but the original copy, by calling getLocation again, is still the original value. Now, if I use the ref return, I've got my getLocation by ref method here. This is returning back a reference to the original value. But I'm saying copy this into a point. So this is going to make another copy of that, because I'm saying this is an actual point struct here. So we're going to get the same problem. I can set the value locally to 12 on my copy, but the original value is still the same on getLocation by ref. And so if I run that, we get a green test, and we can see that we've been working with a copy. What we have to do is we have to use the ref keyword when we're defining the variable and when we're calling it. And now I'm going to get back a reference to the actual to the actual struct itself. So I can make the change to my local reference, and now if I check, then we're going to see that it's still the same value. So now I can pass around references of the types. It also allows me to do kind of really weird things. Like I can have a method call as the left-hand side of an assignment. So that doesn't seem to make any sense, but it does. So what I'm doing here is I'm saying, get me the location. It returns back the reference to the location, and I'm just replacing it with a new point there. And so I'm overwriting the value and setting it to a point of 4242, and there we go. It works. So that's kind of weird. You don't necessarily want to have a method as a left-hand side of an argument, but you could equally there have that returning back the element of an array and be able to, in place, update the contents of an array. Okay, so that's cool. So we've got the ability now to return back references to value types and be able to modify those and work with that. But we possibly don't always want to be able to modify things. That could be a little bit weird. So for example, I could have a reference to an origin point of 0, 0. And I could return that back as a reference, but because it's a reference, I can now overwrite that, and I could move where my origin is, which is probably going to be a bad thing for a game, because all of a sudden, everything's going to be in different places to where it expects to be. And so there's a new feature as well, which is a read-only reference. And so you can use the ref read-only keyword as part of the declaration of the property, and also of the variable, to make sure that the returned value is read-only and can't be modified. But one thing that happens here, this is great, but one thing that happens here is that when you call a method on this returned read-only struct, the compiler enforces the read-only by making another copy, because it doesn't know what your method is going to do. The method might change internal state, and so it has to make a defensive copy so that you know that you're not changing anything. We have a similar problem with another feature, which is in parameters. So we've already got the out parameter and the out modifier and the ref modifier for function and method arguments. We've also got the in modifier as well, and this allows us to pass a value in and treat it as read-only. So it can give it to a method. Here is a reference to a value type, but it's going to be treated as read-only. So it's passed by reference. The method can't modify the original value, but because the compiler doesn't know what the methods on that struct will do, it has to create a defensive copy before you call anything. And so there's another feature again which works around this, and this is the read-only struct option. And here you can tell the compiler that this struct is going to be read-only. And if you define something as read-only struct, and that the compiler will insist that all of the fields are themselves declared as read-only. And so it gives you proper immutable structs. And now the compiler can know that because this struct itself is read-only, it knows that any methods that you call on that struct are not going to change internal state. And so it doesn't have to create this defensive copy anymore, and so that's then another small boost for your performance. Again, it's a micro-optimization, but it can be useful. And the big thing to point out as well is that this is all working with the existing CLR. There are no changes required. This is all just compiler stuff. This is all things that have been able to do in the CLR up to date, and the only changes required are changes to the compiler. Okay, so there's one last feature which 7.2 added, which is a big one. It's also perhaps a little confusing. This is the idea of a ref struct. So this is declaring a value type that can only be allocated on the stack. So normally value types can be part of a class declaration. So I could put a point in a class, so my enemy class, for example, could contain a point value type. But you can declare a ref struct which can't. It doesn't work like that. It can only be used on the stack. So this puts in a whole bunch of constraints on what you can do with this particular value type. The big one is that it constrains the lifetime to the calling method because it can only live on the stack, and once the calling method is done, it gets thrown away. But there's other things as well, so it can't be boxed, it can't live inside another class, and so on. So it has very limited use cases. So you can use it for working with stack alloc memory, memory which has been allocated directly on the stack. But the big use and the big reason for introducing it was for span of t. And span of t is a really cool feature and is something that you are much more likely to use in your code than perhaps some of the ref semantics which we've talked about so far. But it's all built on top of each other. So what is span of t? Span of t is a new type, and it unifies the way of working with any kind of block of memory. So anything that looks like an array or a string or something, anything which uses a single block of memory can be represented as a span. So this can be arrays, strings, native memory, memory allocated on the stack, and so on. It provides us with array-like APIs for working with these blocks of memory. Basically, it gives us indexes. There's also a read-only span type, which provides us with a getter only. You can't set it, so it's a read-only view of something. And it's type safe. Each element of this block of memory is of type T. When you try and get something out, you get an instance of that particular type. And you also get array-like performance. It's not quite as performant as arrays, but it is very, very close. The newer versions of the runtime have special support, which makes it very, very close to array-like performance. Excuse me. That is very useful then. You've got great performance while having something which looks very much like an array, but on lots of different types of memory. The other really cool feature it has is slicing. You can create a new span as a subsection of an existing span. So if you have a span with a block of memory like that, you can then say, I want a new span based on a subset of that data, and there's no allocations as part of that. So that's great. For example, if we think of strings, if you try and get a substring right now, you're going to allocate it, creates you a new string. But now we can use spans to be able to give us a substring without having to allocate something. So the implementation of this is a value type, which is useful because I've just spent a while talking about value types. It gets shipped in the system.memory NuGet package for .NET Standard 1.1, which is the .NET Framework 4.5 and above. I think it comes as standard as part of .NET Standard 2.1. I forget now. As well as the type itself, it gives you a whole bunch of new APIs and overloads in the base class library. So new extension methods which will allow us to work with this type. So you can convert a string to a span. You can create spans from streams as part of parsing text and so on. And all of these APIs have significant use of the ref semantics which we've just been talking about. And the big thing is they're all allocation free. So there are several types. There's span of T, read-only span of T, and there's a memory of T as well, which is a way of representing these blocks of memory which can be put on the heap and so on. We won't look at that today, but that's some homework for you. And there are two versions as well. There's a portable version and then there's a fast version. The fast version requires runtime support. The portable version, however, can run on older versions of .NET. So the portable works on .NET Standard 1.1 and above. That's the .NET Framework 4.5. And it's important to point out that portable is not slow. It's not as fast as arrays, but it's still good performance. And the way it's implemented is that you have three fields. You have a reference to the original block of memory. You have an offset within there, and then a length. And that will tell you then the slice of the data that you're working with. This portable implementation is slightly larger than the fast version, and so dereferencing, getting your data out of it is slightly more complex, but it's just a really small overhead. The fast implementation requires runtime support. It's built into .NET Core 2.1, and basically the runtime recognizes this type. The implementation only has two fields. It has an internal pointer into the block of memory, so instead of keeping the start of the block of memory, it keeps an internal pointer to there, and then the length. So it's slightly smaller, and accessing data is slightly faster, but again, tiny. The important thing is that the runtime knows about the types. There's specific optimizations in the JIT which will help with this. So for example, right now for arrays, the runtime knows it can ignore some bounds checking for arrays in loops because it already knows that the loop itself is not going to go over the length of the array. The runtime applies the same optimizations to span of T as well. And so you get basically array-like performance. So what does this have to do with ref struct? The whole point of it really is there's a few reasons. Firstly, it's all about thread safety. We need to be able to update all of the fields of a span of T at the same time. So we don't want to be able to update, we don't want it so that when we try and update one field, the thread gets interrupted, we go off and do something else, and accessing data goes wrong, and it would all be horrible. And the whole point is performance. For this, we can't put locks in there. If we put locks in there, it's going to kill performance. The internal pointers that are being used are expensive. and they require special garbage collector tracking there, and having too many of those is going to be is too expensive to handle. But the big one really is if you want span of t to work with stack allocating memory, you can't put it on the heap because that just isn't going to work. So the easy solution is to use the ref struct. So span of t can only be allocated on the stack, and it's got a constrained lifetime and single thread access. If it's allocated on the stack, it can only be accessed from that particular thread. Okay. Right, so I have some examples of span here. So for example, I've got some data at the top, creating a string and an array of numbers. And the first one here is with a string. I can use the asSpan extension method to create a span based on my string. That returns us back a read-only span of characters. And then I have a bunch of helper methods and properties that I can use on this span to get me the data. And I can then do work with this without having to do any allocations. So I can do span.length to make sure it's the same. I can do equality to compare against another read-only span. And because it's a span of characters, I can pass in what kind of string comparison I want to do. And things like starts with as well. And if we run that, we can see we're getting green tests, and we're all good. I can then do, I can use the slice method here as well to say, give me from character 6 to the rest of the string there, return that back as a new span. And I can do the same thing here. Again, I can check for the length and confirm that it's the right length that I expect. I can do string equality on that, again, without having to do work with substrings and allocating data here. I'm just looking at that particular slice of the span. Let's just run that one. Yep, and we're green. And we can do a similar thing with numbers as well. So I can have an implicit conversion between a numbers array, that's just an integer array, and I can just assign it to a span of int, and it gets implicitly converted. And then I can do a slice there, and again I can get a subsection of that span. So it's just going to be 5 elements of the span there, and I can assign one of the values there, and then I can assert that the value itself has been changed. And we can run that, and again, we're green. But the best thing is, it's all allocation free. So I have a simple kind of test here then to check for how much memory is being allocated here. I get the current amount of total memory. I make sure that no garbage collections are going to happen during my during this particular time. I run the tests again, and then I get the current amount of memory there. This isn't a perfect test, but it is good enough for what we've got here. And if I run that, again, we're green. We get to see that we've allocated 0 memory as part of this. So we can do substrings, we can do segments of an array, allocations, we can check, do string equality, length, and so on, without having to do any allocations. This is great for things like parsing. So if you can imagine parsing the HTTP headers in a web request, we can do all that now. Instead of having to split those down into lots of different strings, we can do that purely as just one allocation. And the same with JSON as well. So you could have a JSON API, which instead of having to split everything down into a lot of strings to return you back as you're parsing, you can then just do the parsing there and actually only allocate the strings for the data that you want to get out of it. And that basically brings me to the end of everything that I wanted to show you. The reference semantics is very, very useful. It's going to allow you to reduce the amount of memory that you allocate by using value types and passing value types around and working with those, enforcing read-only or allowing them to be mutable. And it also then allows us to use the span of t feature there, which is going to be very, very useful for lots of cases, not only for parsing, but for many things there. And so there are a number of links here which are really useful. The top one, the documentation for all of the sort of reference semantics with value types there is very good, and it's worth a read there. And then there's a number of things about span of t and understanding how you can use that and what it does sort of under the covers. And finally, of course, then is value task, which is, again, very, very useful ways of using value types as part of your tasks, as part of your asynchronous calls. So that brings us to the end there. We've got 5 minutes left. If anybody has any questions, please shout out. We have a question.
You said that when we have lambda expression, it allocates new memory to get all local variables into class, to enclose them. And C#7 introduced a new feature when we can declare a method inside other method.
Yes.
Will be there any allocation or not?
Yeah, there will still be some allocations. So yes, so you can, where you currently have a closure, the compiler will rewrite that to capture local variables into a class, allocate the class, and call a method on that data. Local functions, which are the declaration of a function inside a function. The type which is used to capture all the local variables that are being used is actually a value type. And so from that point of view, if you make the call, the value type itself will be stored on the stack, and so there won't be an allocation going on there. However, there might still be an allocation for delegate usages. So it depends on how you are using your local function. If you're trying to pass it in as a function to something else, as a parameter to something else, then there's going to be delegate instances created. So again, it's one way you have to measure. Local functions can reduce the allocations, but they might not get rid of all allocations. It depends how you're using it.
Okay, thank you.
Okay.
Okay, guys, who wants to begin next?
Hi, thank you. I have a question about your advice to measure. Can you share your best practice, how you measure allocation?
Yes, funnily enough, JetBrains has some tools which can help you with that. It's, thank you very much.
Oh, really?
Yeah. I have stickers as well, by the way. Yes, so we have some tools for measuring and profiling, and that wasn't the whole setup of me saying, please measure. The important thing is the measuring, whichever tool you use. But yes, we have .trace, which is a performance profiling tool. That has a very, very cool timeline view, which captures information, and then you can sort of filter. You can apply lots of different filters on it, and one of the filters you can apply is allocations. And so it can show you where allocations are being used, where allocations are being made, and how much, and so on. And then, of course, there's .memory, which is memory profiling as well, and it'll show you a whole bunch of information and data.
Okay, thank you. Hope you have free subscription.
I have a free subscription. I'm afraid, you know, I also have a mortgage, so.
Yeah, thank you for your presentation. The question is regarding maybe not about the amount of allocations which we have in our programs, but rather than in amount of memory which may be consumed by already allocated objects. So the question is it enough not to have just a lot of subsequent allocations, or we also need to ensure that the total amount of objects which are stored in memory, not necessarily creating the new ones, should be the lowest, as low as possible. Is it affect performance just as the amount of allocations which you described during your presentation?
Do you mean does the number of objects in memory affect performance? Yes, it does. I don't have any hard data to give you. But it's one of the interesting side effects of, say, being a 64-bit process versus a 32-bit process. If you're a 32-bit process, you start to hit the limit where garbage collections happen frequently, faster. If you have a 64-bit process, you can go for longer before garbage collection happens, but garbage collection can take longer. Did that make sense? So if you have a 32-bit process, you've got 1.5 gig of data to work with, and then garbage collection is going to start happening a lot. But the garbage collector only has to work with 1.5 gig of data. Whereas if you've got a 64-bit process, you've got however many gigs that is of data before it really starts going, but the garbage collector has to work with more data to work with. So I would say, yes, the more objects you have in memory, the more work the garbage collector has to do. But again, I don't have hard data on that.
And if we have a choice to reduce the amount of allocations or reduce the total memory allocated in our program, I mean in the amount of objects which we have, what should we start from?
Start from measuring. It really is as simple as that, because it depends. You know, I had a case a couple of days ago where working on a project. It is working in Rider, which is opening a solution and doing some stuff with Unity, which I was working with. I'd written a feature whereby during the process of opening a project, my bit of code was allocating 6 gigabytes. And it's putting a little bit of caching in there. It now only allocates 100 meg. And so, again, that was all about throughput. It was all about reducing the garbage collector, and it kind of just makes it a bit faster because instead of having to calculate everything again and again, it's already got the data there. And so, yeah, that was all through measurement, you know, because the program opened fine. It wasn't really slow to open. It was just doing a lot of work while opening. By measuring and seeing 6 gigabytes, that's probably a lot of memory. And reducing that, it's better, but it's not necessarily visibly better, if that makes sense. Okay, so again, it depends. Measure it and see what needs to be done. There's no kind of hard and fast advice to say, always do this. Okay, I think we're done. If there are any more questions, I'll be out the back there, and we can carry on, but happy to talk and ask any more questions. And other than that, thank you very much for coming.